what happens? So in the LHC, you insert these beams of protons or the lead ions, okay? And you make them collide. So you insert them in two different directions, clockwise direction and anti-clockwise direction. And you make them collide at 4 specific points. And to study what happens in these collisions, we have constructed 4 big experiments surrounding these 4 collision points. One of these points is Alice. Okay? And now we are going down about 65 meters underground to see not only Alice, but we are fortunate enough to see also a part of the LHC itself. Okay? So we will first make a stop at the LHC. Please follow me. So, what you see here is a part of the LHC itself. Okay? So, if you remember, the picture of the LHC is a circular ring, which is about 27 kilometers in circumference, right? Yeah. Now, you can understand it is very sophisticated and complicated machine. Why? Because you are inserting these beams of protons and lead, protons or lead, at a very high energy, and you want to collide them at specific points. So you need to have a very, very precise control over these particles, because you have to move these particles at a very high energy, accelerate them, and you have to guide them in this circular ring and make them collide at a very precise point. Now this control is done by the superconducting magnets. Okay? So the main part of the LHC consists of these magnets. There are different types of magnets. The blue ones which you see here, they are called the dipoles. They are used to give a direction to the particles, these protons or nucleons of lead. So, where there is a curve, you have to move these particles in this curve so that they remain in this circle. This is done by these dipole magnets. Okay? And when these particles, these beams arrive near the collision points, it's a straight section of the LHC. It's a bit straight. You see, it looks straight, right? Because at the point of collision, it enters, it is curved here, and it becomes straight and enters in the collision point. Now, before entering the collision point, there are some different type. There is another type of magnets. Those red ones which you see there, they are called Quark-Gluon-Plasmas. What is the function? Before the beams enter the collision point, they are focused, because the point is very small, precise point. So they are focused into that collision. And though that focusing is done by these red Quark-Gluon-Plasmas. So we will move towards the collision point, which is in Alice. We'll stop here.
Ja, ich sehe sie schon. Ich sehe sie. Ich kann sie sehen. Siehst du?
So,
I can see her. Alice.
so you are going to put this on YouTube, right?
Yeah, okay.
Okay. So we'll just wait for our friends there. So as I told you, these magnets are superconducting magnets, and superconductors are superconductors only at very low temperatures. Okay, so these magnets are maintained at a very low temperature. It's about 1.2 Kelvin. Okay, and you know 0 Kelvin is the lowest possible temperature you can attain, which is about -273 degrees centigrade. And here we maintain these magnets by liquid helium at about 1.23 Kelvin. The temperature of the outer space is about 1.7 Kelvin. So when you go back home, you can tell your friends that you have visited the coolest place in the universe. LHC is really cool, right? So please follow me. So you should send me this link of YouTube.
Yes.
Okay.
Mach mal ein Bild von mir.
Ich kann jetzt nicht, Schatz. Das ist alles Video. Ist aber doch besser.
Okay. So, this is Alice. Isn't she impressive?
Yes.
She's very impressive, right?
Yes.
So what happens here? Down this tunnel, you saw these red magnets. So the beam comes inside from one direction, from this direction. Now these structures are detached because of maintenance. It goes inside that small circle there. See that small circle there? Yes, there's usually a tube there. So the beam is going inside, and the other beams which come from the other direction, they also come in, and the collision occurs exactly in the middle of this whole structure. Okay? So why you want to collide these ions? Because lead ions are what? They are lead nucleus. So in the nucleus, what do you have? Protons and neutrons. Now these protons and neutrons are not fundamental particles. What do you mean by that? You mean that these protons and neutrons are made of some smaller particles. There are smaller particles inside them. What are those? They are the quarks. In protons and neutrons, you have three quarks together held by gluons. Okay? Now, these three quarks, they always stay together. In nature, you don't find a single quark separately. They are always together. And it takes a lot of energy to break them, to separate them.
What is it, trees?
Three. And it takes a lot of energy to separate them. And that's what we try to do in Alice. If you collide them at a very high energy, you can separate these quarks and gluons. Why is it interesting? Because you can create a new state of matter, which is called the Quark-Gluon-Plasma. So it's a plasma where quarks and gluons are floating separately. And why is it interesting? It's interesting because according to the Big Bang theory, just after the Big Bang, that means just after the birth of the universe, just after means few microseconds, 10 to the power -6 seconds, few microseconds after the Big Bang, few microseconds after the birth of the universe, the state of the universe was Quark-Gluon-Plasma. So if you can create the Quark-Gluon-Plasma and we can study it, then we can have some understanding of our origin.
And is that the main point of this?
Yes.
This is not about the expression. This is about the beginning, the Big Bang.
Yes, yes. It's to recreate the state of matter which was the form of the universe just after the Big Bang. Okay? So it's really interesting to understand, go back in time and understand our origins. If I ask you how old are you, I think you will not be offended if I ask you, but we all know the answer, more or less. We are all as old as the universe itself. Every atom, as the famous saying goes, every atom in your body was once a part of some stars. Okay? So please follow me.
Sag ich auch immer. Beeil dich. Ach, die nächsten kommen. Das ist ein Ding. Wir schlafen die Finger ein.
So our aim was to create the Quark-Gluon-Plasma and to study it. How do you study it? So you are colliding the ions, and the collision, we want to study this collision. How do you study this collision? You construct these instruments surrounding the collision point. What are these instruments? They are the particle detectors. So they are capable of, there are different kinds of particle detectors, and they are capable of measuring different properties of different particles. Okay? So measuring these properties of the particles which are coming out of the collision, we can understand about the nature of the collision, what happened actually in the collision. So if you see this big structure, the red one is a big magnet. It's a solenoid magnet, and this structure here on the two sides, they are the doors of the magnet. During the experiment, these doors were closed. Each of these doors weighs about 500 tons, and the whole magnet weighs about 7,000 tons. Okay? And inside this magnet, you have these different particle detectors, which helps us to measure different properties of the particles which comes out of this collision. Okay? So we will go to the other side of the experiment. Please follow. So, as I told you, there are different types of particle detectors to study the different particles. Okay? So inside this red structure, we have, which is called the central barrel of this experiment. It is made for a specific purpose to study specific particles, specific properties of specific particles. Now there are some other particles which come out of these detectors undetected, but we want to study them. One of those particles is muons. It's a fundamental particle. Okay? And this structure which you see here behind is called the muon arm of the experimentalis. Okay? So you have the central barrel and the muon arm. And this muon arm is designed specifically to study these muons coming out of these collisions. And you see these lines, these structures in layers. So these are the different stations of these detectors. What do they do? When the muons come out, there is a filter just after the magnet. So this filter blocks everything except the muons. Muons come out. This blue thing which you see, it's a dipole magnet. Probably it is the world's largest dipole magnet. Now what it does, these muons come out in pairs, positive and negative. So this dipole magnet separates the positive and negative muons. Okay? And you have a different trajectory for the positive and negative muons. These muons passes through these detectors, and these detectors, like many other detectors inside the central barrel, they can detect the position where this particle passed. They can measure the momentum, the energy of these particles. Okay? And once you get the position in different layers of these detectors, you can reconstruct the trajectory of the particle. And once you do that, and once you do these measurements, you can understand, you can try to understand. So these are the effects we are studying, and with these effects we try to understand the cause, which is what we do in ALICE. So different detectors study, make different measurements of different type of particles, and we collect all the data from all the detectors, and the physicists analyze this data. They know that this detector measures this type of particles, this type of properties, and we try to create a picture of what happened in that condition. Okay? Please follow me. On your left, please.
Ja. Der nimmt nicht mehr auf.
So, one more thing before we go is this. Just one important thing. These particle physics experiments are not just particle physics experiments. It's much beyond particle physics experiments. Because while you construct these experiments, you do a lot of development in technology. There are a lot of technological developments in electronics, computers, in mechanical engineering. They are huge. In many other sectors, we do these developments, which was done while constructing these experiments. And there is a dedicated department in CERN, which is called the Technology Transfer Department. They facilitate the transfer of this technology, which was developed for these experiments, to be used in other fields. One of the prime examples is medical imaging and medical physics, where you use cancer therapy, radiotherapy to treat cancer and all. A lot of technology which is developed for these experiments are used in those fields. Please follow. So unfortunately we didn't have much time to explain you everything, but upstairs there is an exhibition where you can see different parts of the different detectors which are used in ALICE, and our colleagues can explain you how these detectors work. There are different types of detectors, and I can assure you they are really fascinating how they work. It was a pleasure talking to you. Thank you very much.
Thank you.
What?
Do you work on this normally?
Yes. We are fortunate that she actually was the run coordinator for the last year. She was the head responsible for the running of this experiment last year.
Did you find anything?
We took a lot of data and we are analyzing. So we published already a lot of papers, and so we have interesting results.
Yeah.
Und der Rashi spuckt ja Pali über sein. Tschüss. Das war